Hi everyone, welcome back to Tech Mastery Guru, where we decode technology, careers, and strategy to help you stand out. In this video on electronics in EV and EV charging infrastructure, we will explore the key components and systems that power electric vehicles and their charging ecosystem. Our agenda covers common terminology, the history and types of EVs and chargers, power flow diagrams, charging station details, communication protocols, and new charging technologies, as well as how to initiate charging and make payments. Let's begin with common terminology in the EV ecosystem. We'll define terms such as EVSE, CPO, EMSP, OBC, and CSMS, which are essential for understanding EV charging infrastructure. The history of electric vehicles dates back to 1832 with Robert Anderson's invention. After being overshadowed by gasoline cars, EVs saw renewed interest in the 1990s, with models like the GM EV1 and later the Tesla Roadster, paving the way for today's growing popularity. There are different types of electric vehicles. Battery electric vehicles, or BEVs, are purely electric with zero emissions and a typical range of 200 to 400 kilometers. Plug-in hybrid electric vehicles, or PHEVs, combine a battery with a gasoline engine, offering a longer range of 400 to 600 kilometers. Continuing with EV types, hybrid electric vehicles, HEVs, use both an electric motor and a gasoline engine, primarily for short and long distances respectively, with lower but not zero emissions. Fuel cell electric vehicles, FCEVs, convert hydrogen to electricity, offering zero emissions and extended range, though they are currently more expensive. When it comes to charging, Level 1 chargers are basic home solutions, using standard outlets and offering a slow rate suitable for overnight charging. Level 2 chargers are more common for homes and public use, providing a faster charge with a 230 volts AC supply, and professional installation is often recommended. For faster charging, DC fast chargers, or Level 3, provide high-speed power from a DC supply, achieving 80% charge in about 30 to 45 minutes. Ultra DC fast chargers represent state-of-the-art technology, using even higher power DC to deliver over 600 kilometers of range per hour, reaching 80% in just 15 to 20 minutes, primarily for premium EV models. We continue to explore high-speed charging. DC fast chargers, also known as Level 3, provide rapid charging for road trips and public stations, using a DC supply for an 80% charge in 30 to 45 minutes. Ultra DC fast chargers offer even quicker charging times, typically 15 to 20 minutes for an 80% charge, leveraging very high-powered DC supply for premium EVs. EV charger connectors vary significantly by region and charging type. This slide illustrates the different AC and DC plug names and types used in North America, Japan, Europe, China, and India, highlighting the diversity in global charging standards. This diagram illustrates the scheme of a battery electric vehicle. It shows the flow of power from the charging plug to the onboard charger, then to the battery bank, and finally to the power converter, motor drive, electric motor, and transmission, propelling the wheels. Here we see the key parts of a battery electric vehicle. This includes the charger port, the traction battery bank, the onboard charger, the battery converter, auxiliary battery, electric motor, motor drive, and transmission, all integrated to power the vehicle. Power electronics are crucial in electric vehicles. This diagram shows how a single or three-phase power supply is converted for charging the batteries, and how the battery's power is converted and managed by a bidirectional converter and motor drive to power the three-phase motor, transmission, and wheels, along with an auxiliary supply. Embedded systems are vital in electric vehicles. They encompass a wide range of functions, including adaptive cruise control, airbags, climate control, and traction control. These systems contribute to user experience through infotainment and digital cockpits and are supported by advanced hardware and telemetry for software updates and data communication. This diagram visually explains AC and DC charging concepts. AC charging typically involves an onboard charger within the vehicle, while DC charging utilizes an off-board charger at a DC fast charging station. Wireless charging options are also depicted, showcasing evolving technologies. This slide illustrates the AC-DC EV charger power flow. For Level 1 and 2 AC charging, the power flows from the grid to the EVSE, then through the vehicle's onboard AC-DC converter to the battery pack. For level 3 DC charging, the EVSE contains the AC-DC converter, and the power flows directly as DC to the battery pack, bypassing the vehicle's onboard converter. This detailed diagram outlines the components of an AC charging station for level 1 and 2 chargers. It illustrates the power supply, regulator, measurement subsystem, and host processing subsystem, all working together to manage and control the charging process to the J1772 cable. Pilot wire communication in AC chargers is essential for safe and efficient charging. It involves a sequence of voltage signals and pulse width modulation between the EVSE and EV to establish connection, determine current availability, initiate charging, and monitor the process until completion, enhancing safety and synchronization. DC charging stations, commonly known as level 3 chargers, involve a more complex power conversion process. The diagram shows 3-phase AC input, undergoing active AC conversion and power factor correction to 400 volts DC. This is then further converted and regulated by a DC-DC stage with communication via CAN before delivering power to the vehicle. This slide presents the end-to-end EV charging ecosystem, illustrating the intricate network of various entities. It shows how EV cars interact with charge points, which are managed by charge point operators using protocols like OCPP 1.6. These CPOs, in turn, communicate with electric mobility service providers and distribution supply operators, forming a comprehensive system for EV charging. Several protocols are used in EV charging to ensure interoperability and smart functionality. OCPP is a widely adopted standard for charger management system communication. ISO 15118 supports bidirectional charging, while OSCP is a newer protocol for the same. OCPI aims for interoperability, and OpenADR enables demand response programs. EV roaming refers to the interoperability of EV charging networks, allowing drivers to charge their vehicles across different charging providers without needing multiple accounts or apps. This enhances convenience and expands the accessibility of charging infrastructure for electric vehicle users. New technologies are emerging in EV charging. Wireless inductive chargers offer cable-free convenience through electromagnetic fields, ideal for various applications. Battery swapping stations provide rapid battery replacement, significantly minimizing charging time and addressing range anxiety for specific EV models. V2X, or Vehicle to Everything, is an advanced communication technology that allows electric vehicles to communicate with other vehicles, infrastructure, pedestrians, and the grid. This capability enhances safety, traffic efficiency, and opens possibilities for vehicles to supply power back to the grid. To start EV charging and make payments, first, find a station using an app. Plug in your EV, then initiate the session by scanning a QR code, entering a code, or using a payment app. Finally, pay with your preferred method and unplug your EV once charging is complete. Thank you for watching. We hope this video has provided valuable insights into electronics in EVs and the charging infrastructure. Please follow Tech Mastery Guru for more informative content.